Okay. Our next speaker is Viraj Pandya from Columbia University.
Okay, thanks, Steve Chang. So hi, everyone. My name is Viraj Pandya. I am a Hubble Fellow at Columbia University in New York. And it's great to be back here in Santa Cruz as someone that got his PhD here just 2 years ago. So I'm very excited to share brand new constraints on the 3D shapes of high redshift galaxies observed with JWST. And I promise by the end of this talk I will have convinced you that galaxies going bananas is in fact an apt description of our results. This is work done primarily in collaboration with Hawen Zhang and Mark Huerta's company, who are at the workshop this week, as well as Karthik Iyer, another Hubble Fellow at Columbia, and then with the CEERS collaboration more generally. So we've already heard that it's been an exciting first year for JWST for many reasons, one of which is that it has enabled many interesting studies of the morphologies of the most distant galaxies. And so here is just a listing of a few recent papers that have used a combination of visual classifications and parametric and non-parametric morphological modeling and machine learning methods to probe the diversity of galaxy structure at the earliest epochs that we can observe with JWST. And what I want to emphasize is that pretty much all of these existing JWST studies have essentially focused on the 2D projected properties of these high redshift galaxies. And in this talk, I'm going to try to convince you that we can actually start to get a handle on the intrinsic 3D geometries of high redshift galaxies observed in existing JWST data. And in particular, I'm going to focus on observations from the CEERS Early Release Science survey. So here's a beautiful image of the Big Dipper. And next to the Big Dipper on the night sky, there is a tiny rectangular patch, which is known as the Aegis survey. And that, in turn, is the basis for early release science observations with James Webb by CEERS. So if we zoom into that little rectangular patch, you, of course, see a beautiful population of galaxies. And these are, of course, three-dimensional objects projected onto the two-dimensional sky. And we want to use the information about their projected shapes to infer something about their 3D geometries. And that is, of course, a very complicated problem, but we can make some headway by assuming that in 3D, every galaxy can be classified as one of three kinds of ellipsoids. So first you have spheroids, where the three axes are roughly equal. And then you have oblate, or disky ellipsoids, where one axis is significantly flattened and the other two axes are roughly similar. And then you have a third class of ellipsoids that we don't usually talk about for some reason often. These are known as prolate ellipsoids, where two axes are significantly flattened and you have one axis that is significantly elongated in 3D. Or in terms of my favorite analogy these days, you can just say that galaxies are falafels, pitas, or pickles. Now, observationally, you only see each individual galaxy from a single viewing angle, so you can't infer much about its 3D shape just from the imaging alone. But there's a very powerful technique going back 100 years actually to Hubble himself, where if you have a population of galaxies with similar masses and redshifts, you can use the distribution of their projected shapes to start to infer something about their 3D geometries. And these techniques use a very relatively simple measurement. So for every galaxy in your image, you measure the best fitting ellipse. And then you characterize that ellipse by the ratio of the short axis divided by the long axis. And when this axis ratio is small, it means that galaxies are elongated in projection. And when this axis ratio is large, it means that galaxies are round in projection. So you can go and measure this best fitting ellipse for all the galaxies in your image and then start to bin by mass and redshift and other things and look for trends. And many authors have been doing this over the past century. But my favorite paper actually is from 10 years ago by Arjen van der Wel, who nicely showed that for massive galaxies at any redshift, including redshift 0, the distribution of their B over A axis ratios is relatively uniform or flat. And this is because we think that massive galaxies are roughly a mixture of oblate or disky ellipsoids as well as spheroids. Now, if you make this plot, this kind of distribution for high redshift, low mass galaxies, it looks fundamentally different. So here's an example of one of these high redshift dwarf bins. This axis ratio distribution is asymmetric. It's skewed towards small axis ratios with B over A peaking at about 0.3 or 0.4. And so you can ask, well, for this high redshift dwarf population, where are all the dwarfs that would appear round in projection? So before discussing some solutions to this puzzle, I want to switch gears to JWST, and in particular the CEERS survey, which you'll hear more about from Dale Kosevsky this afternoon and many others this week. Here's a nice schematic showing the various pointings with the JWST instruments in that same rectangular field next to the Big Dipper that I showed you a few slides ago. Now here is on the top some of the deepest imaging that we had for these elongated low-mass high-redshift galaxies with HST, 50 hours of staring at the same patch of sky with the candle survey. And you can see hints of elongation. And then with less than an hour of observing time with CEERS on JWST, you can see so much more substructure in the same galaxies. And in some cases, you can see that previously there may have been a companion nearby that was blended together with the main object, maybe making it appear artificially elongated, whereas now the improved spatial resolution and sensitivity JWST allows you to resolve these distinct sources nearby. So we can use this exquisite data with its improved sensitivity and spatial resolution and wavelength coverage to go to higher redshifts and revisit this puzzle. And in particular, when we go and measure the distribution of axis ratios for high redshift low mass galaxies, in the CEERS imaging, we still see, despite the improved sensitivity and resolution of James Webb, we see the same asymmetric distribution for B over A skewed towards small axis ratios. Now, this is the 1D distribution of B over A, and it was shown in a nice paper in 2019 by Hao and Zhang that it's more insightful to actually plot the 2D distribution of B over A as a function of size. And you can see, again, for this high redshift, low mass population, it's tracing out a particular shape in this diagram, and in fact, we say it's tracing out a banana shape. And the fact that these galaxies are tracing out a banana shape in this diagram is telling you something about their 3D geometries. So let's go back to our three classes of ellipsoids. A population that is predominantly made up of one of these three kinds of ellipsoids will leave unique signatures on that B over A versus size diagram. So for example, for a population of spheroids seen from many different viewing angles, they're going to look round from any viewing angle, so they're going to have preferentially high B over A on this diagram. Disks are different because you can see a disk face on, it's going to look round in projection with high B over A. You can look at a disk edge on, and it'll have a low B over A, but in fact, you're equally likely to observe a disk from any viewing angle. And so you would see, for a population of oblate ellipsoids, you would see a uniform distribution in B over A that trails off at small B over A because disks have a finite thickness. Now, the third class of exotic prolate ellipsoids are completely different. In fact, most of the projections would end up at small B over A and large size, and this is because you're much more likely to observe one of these prolate ellipsoids with the long axis in projection as opposed to directly down the barrel. So we can overplot our favorite fruit, and this is in some sense one of the proposed solutions for this puzzle of why we're seeing these strange axis ratio distributions, initially in HST imaging and now inarguably also in the JWST imaging. Now, this is not enough. You have to actually do some more detailed modeling of the data, so we've written a very powerful, very fast, differentiable Bayesian modeling code. And the basic idea here is you take your observed galaxies, you find the ones that fall in some mass redshift bin, and then for those galaxies, you want to infer the distribution of the 3D ellipsoids that correspond to those observed projected systems. And so we start by writing out this vector where for every 3D ellipsoid, you can characterize it by three numbers, something called the ellipticity, something called the triaxiality, and something that characterizes the size of its longest axis. And we don't know what the distribution of this data vector should be, corresponding to some observed sample in some mass redshift bin, but we can make the assumption that it is distributed as a 3D Gaussian, where the population that you observe, or the sample that you observe, is drawn from a population with unknown mean ellipticity, triaxiality, and size, and unknown covariance matrix. And we can actually fit for these parameters with the existing JWST data. So we've actually gone ahead and written a Bayesian model that assumes a Poisson likelihood for constructing model B over A versus size diagrams and comparing them to the observed B over A versus size diagram with uniform priors on all of these parameters. But we haven't just stopped there. We've actually gone a step further than that. We've actually made this new code differentiable, which means that I can actually compute the gradients of this model with respect to all of its free parameters, and then use a very powerful technique known as Hamiltonian Monte Carlo, which is 100 times faster than standard MCMC. And so you can do this kind of modeling in a fraction of the time that it took you before. So here is again this banana-shaped distribution for this that's observed with JWST for a representative high redshift low mass population. On the left is the observed, and on the right is one Poisson realization of our model, and you can see it looks pretty decent. Now, we don't just get a single best fit model, we get a distribution for a range of allowed models, and in particular, I'm showing here the posteriors for the mean ellipticity, the mean triaxiality, and then the mean size. And you can see, first of all, that they are converged. Different chains are converged despite the small sample size of CEERS, and they are constrained. So in particular, on the top, the mean ellipticity parameter for this high redshift dwarf population is high. It's closer to 1 than it is to 0, and so we are in one of two regimes for these galaxies. They are either oblate, disky objects in 3D, or they are this intrinsically elongated class of prolated ellipsoids. And the way to break that degeneracy is to constrain this intermediate, this other parameter called the triaxiality, which constrains the intermediate axis ratio B over A in 3D. And you can see that our model is pushing us up towards large values of triaxiality, which is what you would expect for a prolate population. Oblated ellipsoids have a triaxiality of 0. Whoops. And so the model is strongly favoring the prolate scenario for the high redshift dwarfs observed with JWST. Now we can repeat this procedure for the galaxies in different mass redshift bins, and then start to plot mass redshift evolutionary trends. And so here I'm showing the prolate fraction as a function of stellar mass at a fixed redshift in the individual panels, and then as a function of redshift for the different panels in this row from left to right, going out to redshift 8 and starting at redshift 0.5. There's different colored lines here. The black and yellow are just used to show that we recover previous results from 3D shape modeling of the full 5 candles fields based on HST imaging in a fraction of the time with our new code. And then the key things are these magenta and cyan lines, which are the results of our model run on 2 different sets of shape measurements of the CEERS imaging, the galaxies in the CEERS imaging, using 2 very different codes, and I can say more about that if you're interested later. But the key thing is that for the low mass population, we see that our model says that the prolate fraction goes from something like 20% out to possibly an astoundingly high 80% out to redshift 8, which is, I think, incredible. This is not an insignificant population. Now, we do see evidence of oblate or disky galaxies at the 40 to 50% level, but this is primarily at the massive end and or at lower redshifts. And this validates many of the previous studies that have used different techniques to look for evidence of the earliest disks. And then we also we also constrain the spheroid fractions in 3D, which tend to be relatively low, except there's a jump at high mass, at high redshift in some bins here. Here is another way to visualize these results, now shown as stacked bar charts. So from left to right is the three panels show the three different mass bins, and then in a given panel is the redshift evolution. And you can see that for the low mass bin, the prolate population shown in blue is just dominant. And as you go to higher masses and lower redshifts, the spheroidal and oblate populations start to kick in. There's one other thing that I can't resist showing, because many of us are interested in the size-mass relation, and with this approach, we automatically constrain the 3D size-mass relation and its redshift evolution. And so you can see here on the top panels is the evolution of the mean sizes of the populations as a function of mass and redshift, and we see the expected trends. And on the bottom is the scatter about this mean size-mass relation, which is remarkably small, and it's consistent with previous work on using HST, and it remains remarkably small at a high redshift. So everyone always asks me, what do these things actually look like? So we've gone in and we've created postage stamps of some of the highest probability candidates for being prolated in 3D. And you can see here some of these objects. They are consistently elongated. They're linear. They're clumpy. In some cases, like in the top right example here, they actually remind me of this long-forgotten class of chain galaxies from the 90s that we don't talk about anymore for some reason. And my key point, my key message in this talk is that these edge-on looking things are way too abundant in number compared to the relatively face-on things that we would expect to see if these were pulled from just a population of 3D disks. Now, we do have some high probability oblate candidates, so you can see some obvious examples here, and then we also have some examples of compact concentrated spheroids. So how might these high redshift prolate systems actually form if that's what they are? So there's been a lot of nice work by Daniel Severino and Avishai Deckel and Joel here showing, based on simulations, that galaxies may look prolate in the observations and maybe prolate in 3D, because if they're forming in dark matter filaments and they're constantly undergoing accretion, minor mergers or major mergers along the long axis of the filament, and so that leads to this consistently elongated stellar distribution aligned with the filament on longer scales. This had many implications if it was true, and one of which I actually explored as a grad student here at Santa Cruz, running a paper with Joel, suggesting that the intrinsic alignments of these high redshift galaxies can be used as novel probes of filaments of the cosmic web at high redshift. So there's one last thing I want to leave you with. And that is that there is one other interpretation that I think is just as exciting and we should consider. And to really drill this last point home, here is the two classes of extremely flattened ellipsoids. On the left is a prolate thing where the intermediate axis equals the shortest axis, and on the right is an oblate thing where the intermediate axis equals the largest axis. Now, in our quest to simplify things as much as possible, we sometimes avoid alternative possibilities, and so there is another possibility here where you can have a very flattened structure, but it would be unusually oval. It's an unusually oval disk where the intermediate axis B is not equal to either C or A, but somewhere in between. And this reminds us of a surfboard, and so I've gone ahead and plotted my favorite Santa Cruz surfboard because we're in Santa Cruz. And so what do the data show? Well, the data clearly imply a transition in the 3D shapes of galaxies as a function of mass and redshift. So you can see, I'm showing you here the distributions of 3D C over A versus 3D B over A for a few different mass redshift bins that are representative. And these boundaries here are these classic divisions between the three shape classes. And you can see for low redshift, high mass bins that the distribution is shifted towards the oblate spheroid part and towards the right of the diagram. And then as you go to progressively higher redshift, like 3 to 8, the dwarf regime at high redshift, you get galaxies ending up towards this prolate region on the left. But if you look closely, actually, even for this distribution here, most of the objects seem to have a B over A that is roughly 2 times C over A, and this is a hallmark of an unusually oval or triaxial population of disks. And so I think this is actually just as exciting to focus on as the prolate scenario, and I think it hasn't received the attention it deserves. And the reason is that many of us are interested also in this idea of disk settling, and we'll hear more about this tomorrow. And there's this idea that disks settle in terms of their vertical thickness from being thick to thin as a function of redshift. But I think these observations suggest that there might be another kind of disk settling in play, possibly where disks settle from being oval at high redshift and become progressively rounder at low redshift. So we should, I think about that more carefully. Okay, so all of this has been a teaser for a paper that will be coming out very soon, so please stay tuned for this paper, and I'll leave my summary slide up and take any questions. Thank you very much.
Very nice talk. Questions?
Thank you, Viraj, for a very nice talk. You mentioned mass redshift evolution of the shape. I wonder have you thought about if it's really a mass trend or a redshift trend? Or maybe it's a peak height trend?
That's a great question. I haven't thought about that yet. We've been focused on making as clear measurements as possible from the observations, and the next step would be to then develop an evolutionary model connecting these different mass redshift bins. So I'd love to talk more about that.
Okay, we can have a quick question, and meanwhile, our next speaker, please come up, set up.
So I wanted to make a point and ask a question. The point is that when we actually simulated this, and you showed an example of the simulations, Severino, Premack, Eckel, what we found was that although the stars tend to be prolate, the gas is usually in a rotating disk. And so if you do measurements of the spectra, and you're looking at emission lines from the gas, you're not going to get the same message that you get from the shape of the stellar population. So you have to be careful about that. Yeah. Did you have a chance to look into any of that?
Not yet, but I did put in, so when we got the second set of CEERS observations last December, I presented a few of the highest probability prolate candidates from HST imaging, and we got a few spectra. So the next thing we'll be doing is looking at emission lines, looking at the spectra to see what else we can infer.